Good morning, everyone. My name is Chen. It is my great pleasure to share my additive manufacturing research with you today. The work has been conducted partly under the financial support of EPSRC First Grant and Early Career Fellowship. Hence, a sincere thank you is given to the UK's Engineering Physical Science Research Council to promote the early career researchers. Selective electron beam melting is similar to another laser-based powder bed fusion additive manufacturing called selective laser melting. Both techniques basically use the powders as the feedstock material and involve the high-energy beam to melt the powders layer by layer. There are two advantages of SEBM over the SLM, which excited me to work on this AM technique. First, the high build temperature achieved by using the preheat step, which helps to reduce the thermal stress induced cracking. Second, electron beam works under vacuum environment, hence limiting the oxygen pickup, which is particularly important to the mechanical properties of the high temperature and intermetallic alloys. We have been primarily working on two materials systems and their mechanical properties, including nickel-based superalloys and gamma titanium aluminide alloys. My talk today is about additive manufacture nickel-based superalloys with a high gamma prime content, over 70%, used for the hot section turbine engines. By identifying the cracking mechanisms associated with this AM process, we developed a scan strategy to mitigate the crack formation in the as-built condition. And we then applied a range of the characterization tools to characterize the microstructures, tensile properties at room and elevated temperatures, as well as elucidating the deformation and degradation mechanisms. Regarding the gamma titanium aluminide research, you will hear a talk entitled Effect of the Scan Strategy on the gamma titanium aluminide-based composite fabricated by SEBM from my student in session 5 on the 9th of September. So, what is the non-weldable nickel-based superalloys? So this term originally from the welding metallurgy community. So the classification of the non-weldable and versus this weldable is based on the aluminum and the titanium content. There have been extensive work focusing on the additive manufactured Inconel 718, which fall into the category of the weldable nickel-based superalloys. This basically motivates me to work on the non-weldable groups, which includes the DZ125 as well as the IC21 superalloys. So as shown in this figure, even with the SEBM process, you can fabricate your materials at high temperatures. We still couldn't remove all of the crack formation in the as-built condition. So those cracks appears along the columnar grain boundaries tend to be parallel to the build direction. And back to the time when the research was performed, a very interesting debate existed as to whether the post-processing route, such as the hot isostatic pressing, short as the heap, is the effective way to remove such a crack. So to this end, heap was used to heal the cracks, as observed in such a SEBM-built nickel-based superalloys. As you can see from these micrographs, we removed most of the cracks compared with the as-built condition. However, periodically, we can still see such a remaining pores in the heaped condition. However, the major problem here is when you apply the heaping to close such a cracks, you lose all of these desirable cuboidal shaped gamma prime precipitate. And hence, we have to apply a full heat treatment involving the solution annealing and precipitate aging to create the cuboidal shaped gamma prime morphology. However, as you can see from these micrographs, you suddenly have a massive number of the cracks reappearing in these micrographs. In addition to that, and such cracks tend to have a much larger crack opening width. So all of this is telling us perhaps a heaping is not an ideal way to close such a crack in the additive manufactured process. So the cracking mechanisms was confirmed with the aid of opening up the crack face together with the SEM fractography observation. So the presence of the liquid film in the cracked face suggests that the solidification cracking is the mechanism. This also means that the precise parameters related to the SEBM was not at their optimum condition in terms of the solidification from the liquid to the solid phases. So using the same method, let's have a look at the fractography after the materials failed, after subjecting to the heaping and the full solution treating and aging. Again, we open up the crack. As you can see here, the liquid film still remained from this micrograph. This means the heaping is not an efficient way to create the essential metallurgical bonding between the materials, although they might seem to close the cracks from the micrograph. So one thing we have been convinced from this preliminary work is the only way to get the crack-free samples would be to optimize the precise parameters. We thereby performed a further design of experiment to develop the mitigation strategy. So the nickel-3 aluminum-based superalloy bar IC21 was subjected to the plasma rotating electrode processing to obtain the pre-alloyed powders for the SEBM process. So we have characterized the powders, including the flowability, packing density, particle size distributions, and all of these properties meet the SEBM process. So in particular, we control the element of boron and zirconium because both were reported and they tend to increase the susceptibility to get the liquid film related cracking during the AM process. So the SEBM samples built per batch contained 6 rectangular shaped samples. So the red hatched region indicates the lower part, which including the sample support as well as the parameter adjustment using the high scan speed. While the blue regions is the sample printing, and by using this kind of the lower scan speed and trying to achieve this crack-free microstructure. So by using this approach and also help us to avoid of the distortion of the sample when you just use this very low scan speed onto your sample. So the left figure showing you the temperature maintained within the chamber. You can see through the build, we operate this SEBM process at a high temperature. In this case, is above 1000 degrees C here. So the design of experiment, the so-called DOE, was performed to search for the precise parameters that allow us to achieve this crack-free microstructure. So this figure is showing you through the whole process, and we maintain a good vacuum condition in the chamber. So the figure on the left shows the crack ratio change initially increase with the increase of the grain width and then decrease with the increase of the grain width. So the key parameters we're highlighting here is a high energy input. So if you can achieve a high energy input, in this case is by lowering the scan speed, you are most likely to get the crack-free microstructure. However, if you use a very low scan speed to increase this line energy input, you will also have this uneven top surface. And this potentially increases the chance to get other types of the defect, such as the lack of fusion defect. So what we did here is we combine this scan strategy, the so-called the high line order, with this lower scan speed, and we can successfully get this even top surface as well as the crack-free microstructure. So by looking at the cross-section longitudinally from the bottom to the top of the build, and we prove we can get this crack-free microstructure in these non-weldable nickel-based superalloys, while this SEBM precise. So as you can see from these micrographs after etching, and we can get these columnar grains, and which is giving you a good continuity in terms of the epitaxial growth. And the very fine columnar dendrite formed in this process can be attributed to the rapid solidification during this AM process. So both the room temperature and the high temperature up to 1000 degrees C has been characterized in terms of the mechanical properties. So as you can see, the properties are as good as the cast counterpart. When I say cast, it means that you do a casting followed by the heat treatment. Okay. And also the tensile properties for both the parallel and perpendicular to the build meet the industry standard. It is also interesting to know when you look at the stress and the strain curves for the room temperature tensile properties, they tend to show a extremely high strain hardening behaviors. So we then use the transmission electron microscopy to observe the dislocation structures, the so-called TEM. Okay, and because from this we can understand what is the tensile deformation mechanisms for these additive manufactured nickel-based superalloys. So these TEM observation areas contains both the gamma channels as well as the gamma prime precipitates. The presence of the gamma prime precipitate can be evidenced from the superlattice reflection under the selective area diffraction. So the STEM and EDX analysis in terms of the elemental partitioning confirms the brighter phases are the aluminum-rich gamma prime phase, while the rhenium, the chromium-rich, as well as the multi partitioning to the gamma channels confirm they are the solid solution strengthening element in these microstructures. So the presence of the high density of the tangled dislocations, as shown by the dislocation pairs here, is consistent with the high strain hardening at the room temperature observed. And also, we can see this kind of the very unique and which is also commonly observed in the cast-made nickel-based superalloys. And when you get the deformation occur, which is driven by this classical superpartial dislocation separated by the antiphase boundaries. So when you view these along the 001 axis, you will see this kind of the orthogonal relationship between the dislocations. So which is the so-called screw or the 60-degree dislocations. These all explain the deformation mechanisms observed in this microstructure. So of course, nothing is perfect and as straightforward as we thought. So as you can see here, along the build direction from the bottom to the top, and we can see there are sort of the different volume fraction of the secondary phases. Okay, so based on the SEM and the EDEX analysis, and we can see more close to the bottom of the build, and they tend to give you a higher volume fraction of these brighter phases. So from the analysis, and we can see they contain the high molybdenum and rhenium, and this is all the element suggesting they are the topologically close packed phase, the so-called TCP phase. And also for these needle-shaped phases, they contain a higher chromium and tantalum here. Again, they are TCP phase. It is known to the nickel-based superalloy community, the TCP phase is detrimental, in particular for the high temperature creep properties. So this forms our future work in this field. So as a conclusion of my talk, the certification crack occurring in the SEBM nickel-based superalloys is difficult to be healed by the heap method. So when we have these crack-free samples and how we achieve these, and we can use an appropriate scan strategy involving a higher line order and lower scan speed. And the mechanical properties of these nickel-based superalloys is as good as the cast counterpart. So the downside of doing this kind of things is we see a lot of the TCP phase, which basically highlights the future work is trying to use the alloy design procedure and trying to optimize the alloy composition tailored for this AM route. So thank you very much for your time and attention. I really miss the face-to-face communication and the conference banquet. And please do get in touch with me if you're interested in the additive manufacturing and structural integrity of nickel-based superalloys. Thank you.